Hello students, we are solving the IB Math A HL past papers and today we will be solving the IB Math A HL May 2021 paper 3 time zone 2 past paper and we will be solving the first question or question number 1 of this paper. As you know, paper 3 will be containing 2 questions. So the second question will be solved in our next session. In this session, we will be solving only question number 1 and you will be getting the links to all the previously solved questions of the other papers in form of playlists in the description area. So without any further delay, let us start answering question number 1. The maximum mark is 31 and it says this question asks you to explore the behavior and some key features of the function fn of x equal to x raised to the power of n times a minus x whole raised to the power of n, where a belongs to the set of positive real numbers and n belongs to the set of positive integers. In subparts A and B, only consider the case where A is equal to 2. And you are seeing I have brought in only subpart A. In fact, this question number 1 contains subparts up to H. So we will be solving them one by one. Therefore, I have brought in only the first subpart, that is subpart A. Consider f1 of x, that means n equal to 1. So the expression will be x to the power of 1, which is x, times a is equal to 2, so it is 2 minus x whole raised to the power of 1 or 2 minus x. Question for subpart A is sketch the graph of y equals f1 of x, stating the values of any axis-intercepts and the coordinates of any local maximum or minimum points. Axis-intercepts means the x-intercepts, the zeros, and the y-intercept. And maximum or minimum points, because obviously this is a quadratic expression, it will be having only a single vertex. So it will be having either a maximum point or a minimum point, and we are seeing the term containing x squared is negative, so the parabola will be opening downwards. It will be an inverted parabola. And we are seeing the zeros as well. X equal to 0 and x equal to 2. These are the two x-intercepts. And you have to get the maximum point. That is what you have to just calculate. And x equal to 0 and x equal to 1, x equal to 2, since these two are the x-intercepts. So the line of symmetry will be x equal to 1. Okay, because it will be halfway between 0 and 2, x equal to 0 and x equal to 2. The line of symmetry will be x equal to 1. The vertex will be on the line of symmetry. So if you put x equal to 1 in this, 2 minus 1 will be 1 times 1 is 1 times 1 is 1. So the maximum point will be 1 comma 1. We in fact do not have to use the calculator. So just let us write that. If you want, you can use the calculator, but I don't think there is any necessity. Okay, so let us write the zeros. Will be 0 comma 0, because when x equal to 0, y will be equal to 0 as well. Hence it is the zeros, one of the zeros of f1 of x, that is the x-intercept, and the other one will be 2 comma 0. And the maximum point is will be 1 comma 1. If you want, of course, you can use the calculator. But I think since we can sketch it without the help of the calculator, you should be doing it without the help of the calculator, because you may be taking more time for the other subparts. This is just the first subpart of the first question. Okay. So now that we know these points, the x-intercepts and the y-intercept, Y-intercept is again this one, 0, 0, and the maximum point we are in a position to sketch the parabola. So it is like this. Okay. So this is the x-axis, this is the y-axis, this is 0, maybe this is 1, this is 2, 3, 4, and this is -1, -2, +1, -1, -2, -3, and we will be having 0, 0 as one of the points, 2, 0 as the other point, the zeros, and the maximum point will be 1, 1, this one. Okay. So now we have to just join them. Okay. Not at all a symmetrical parabola, but anyway. So this is f1 of x. This is 1, 1. Okay, so we have shown the axis intercepts. We have shown the maximum point. So we are done with subpart A and we have got 3 marks. So let us bring in the subpart B, the next subpart. Consider fn of x equal to x to the power of n times 2 minus x whole raised to the power of n, where n is a positive integer and n is greater than 1. Subpart B's question is, use your graphic display calculator to explore the graph of y equals fn of x for the odd values n equal to 3 and n equal to 5, and the even values n equal to 2 and n equal to 4. Hence, copy and complete the following table. Okay, and the table is having n equal to 3, n equal to 5, and this is n equal to 2, n equal to 4, and the columns are number of local maximum points, number of local minimum points, number of points with inflection with 0 gradient. Okay, fine. So first of all, we have to get the graphs of all these 4 in values. Okay, n equal to 3 and n equal to 5. So it will be x cube times 2 minus x whole cube for the first case. Okay, so x cube times 2 minus x. For a and b, it was a minus x, a is equal to 2, so it will be 2 minus x whole raised to the power of 3. Okay, enter. Let us just take the settings from -2 to +2. Better. Okay, Also, I can take, I can just take the x-axis as not from -10 to +10. I can take it from -3 to +3 or -5 to +5 as well. Okay, let me take it as -5 to +5. Better, definitely better. Okay, fine. Now this is n equal to 3. We have to get n equal to 5. So n equal to 5, so it will be x to the power of 5. Let me show you the expression again. X to the power of 5 times 2 minus x whole raised to the power of 5. Okay. So x to the power of 5 times 2 minus x whole raised to the power of 5. Enter, and again I have to change the settings. Okay, let me take this from -5 to +5. And this from -2 to +2. Again better. Okay, so we have got n equal to 3, n equal to 5 graphs, and now we have to get the n equal to 2, n equal to 4 graphs. Okay, so n equal to 2 means x squared times 2 minus x whole square. X squared times 2 minus x whole square. So this is enter. Okay, for this I can again change the settings. I can take from -5 to +5 and 5, and this can be taken from, it is not going below, so I can take this from -1, or fine, -2 is fine. This can be taken up to +3. Better. Okay, and finally we have to get for n equal to 4. So x to the power of 4 times 2 minus x whole raised to the power of 4. Enter. Again I have to change the settings. -5 to +5, and this one is -2 to +3. Better. Okay, now that we have got the 4 graphs, let us go to this one. This one is for n equal to 3. Okay, so now let us come to the questions. We have to just fill in the cells, complete the table. So for n equal to 3 and n equal to 5, number of local maximum points. Okay, this is n equal to 3, x to the power of 3. One maximum point for n equal to 3, and for n equal to 5 also there is a single maximum point. So number of maximum points is 1. Number of local minimum points. we don't have any minimum. We don't have any minimum points. Okay. So 0. Number of points of inflection with 0 gradient. That means for those values of x, the tangent will be parallel to the x-axis. See, for n equal to 3, this is, you see, this is over here. If you sketch a tangent, it will be on the x-axis, in fact. Okay, it will be the x-axis. The x-axis is the tangent for these points. And for n equal to 5 also, we are seeing the 2 points or station points of inflection. That is the point of inflection with 0 gradient. Okay. So we are having 2 points of inflection with 0 gradient for n equal to 5, and also 2 points of inflection with 0 gradient for 3. So we can write this as 2. And for n equal to 2 and n equal to 4, number of local maximum points, this is n equal to 2. Local maximum is this one, 1. This is n equal to 2. This is the same for n equal to 4. This local maximum is 1. Second is local minimum. You see, these two are local minimums, and don't confuse between a local minimum and a point of inflection with 0 gradient. These are minimum points, but if I go to this graph, you see, this is not a minimum. Minimum means it will be moving down, then coming up. But this graph, it is moving down, it is decreasing. Over here, it is just on the x-axis, it is parallel to the x-axis, and again moving down, it is not coming up. It is not a turning point. Okay. So don't confuse between a turning point and a point of inflection with 0 gradient. Over here, the graph is decreasing, and also over here, the graph is decreasing. Same for this part. So these are cases of points of inflection with 0 gradients. But for this one is a minimum, this one is a minimum. If even for these two are minimum points. It is coming down and moving up. Okay. So 2 minimum points. And point of inflection, we don't have any point of inflection for n equal to 2 or n equal to 4. Okay. So this is 0. So we have completed the table. We move on to subpart C. Now consider fn of x equal to x to the power of n times a minus x whole raised to the power of n, where a is a positive real number and n is a positive integer and n is greater than 1. Subpart C says, show that if n dash of x, that is the first derivative of fn of x, equal to n times x to the power of n minus 1 times a minus 2x times a minus x whole raised to the power of n minus 1, and it is containing 5 marks. Okay. So, and you are definite. I think you should be getting these 5 marks because it's just the first derivative. You will be using the product. Simple. Okay. So, if n of x, or let us write if n dash, if n is given over there. So the first derivative. First of all, I am differentiating x to the power of n. So this is n times x to the power of n minus 1 and a minus x to the power of n plus x to the power of n, and this n will be coming down, so it is n times a minus x whole raised to the power of n minus 1. And when we differentiate a minus x, it is minus 1. So this is equal to, I can take n common, x to the power of n minus 1 common. So let us bring out the common factors one by one. N times x to the power of n minus 1 times a minus x to the power of n minus 1. Okay. So what will be within the brackets? From the first term, n times x to the power of n minus 1, that has been taken out. And this is a minus x whole raised to the power of n, but outside we are having a minus x whole raised to the power of n minus 1. So 1a minus x will be inside the bracket. And from the second term, this is minus, so I'm writing minus. And x to the power of n minus 1 has been taken outside, and this is x to the power of n. So I'll be having 1 x to the power of n remaining, and n has been taken out, a minus x raised to the power of n minus 1 whole raised to the power of n minus 1. It is outside the bracket. So I'm having only a minus x from the second part. So this is equal to n times x to the power of n minus 1 times a minus x whole raised to the power of n minus 1 times a minus 2x. Okay. So this is exactly this expression. Okay, so this is this. It is shown. Okay. Coming to subpart D, and we have got 5 marks. State the 3 solutions to the equation if n dash of x equal to 0. That means the first derivative is equal to 0. So if n dash x equal to 0 implies this whole expression n minus 1 and a minus 2x is equal to 0. So n is a positive integer, n is greater than 1, therefore n is definitely not equal to 0. So either x to the power of n minus 1 is equal to 0, or a minus x whole raised to the power of n minus 1 is equal to 0, or a minus 2x is equal to 0. Okay, so this gives us, therefore, either x is equal to 0, from x to the power of n minus 1 equal to 0 means x equal to 0, or a minus x whole raised to the power of n minus 1, n is a positive integer and n is greater than 1, so n minus 1 is not equal to 0, or it is not a negative number. So a minus x should be equal to 0 or x equal to a, or a minus 2x equal to 0. So a minus 2x equal to 0 means a equal to 2x or x equal to a over 2. And since a is a positive real number, obviously the a will be greater than a over 2. Okay. So that is why I'm just rearranging the 3 zeros. So therefore, the 3 solutions are x equal to 0, x equal to a over 2, and x equal to a. Okay. So part E. Show that the point a over 2, comma, fn of a over 2, that means x equal to a over 2, on the graph of y equals fn of x is always above the horizontal axis or the x-axis. And this contains 3 marks, and the expression for fn of x is this one. So, and we cannot use the calculator for this question because a is a variable, so you cannot graph it. Therefore, whatever we do, we have to use the algebra to prove this. So let us first of all find what is fn of a over 2. So let me just write the fn of x expression first. So therefore, fn of a over 2 will be equal to x equal to a over 2. So a over 2 whole raised to the power of n times a minus a over 2 whole raised to the power of n equal to a minus a over 2 is a over 2. So a over 2 whole raised to the power of n times a over 2 whole raised to the power of n, and using the law of indices, e to the power of m times e to the power of n is equal to e to the power of m plus n. Over here e is equal to a over 2 and m plus n, m is equal to n, that means it is n and n, so it will be n plus n or a over 2 whole raised to the power of 2n. Okay, and n is a positive integer. Okay. So since a over 2, or let me write, a belongs to the set of positive real numbers, therefore a over 2 is greater than 0. Okay, and 2n is an even number because n is a positive integer, so 2n will be an even positive number. So 2n is a positive even number. Okay. So the base A over 2 is positive and the power is also positive. Therefore, or so, anything. Okay, since I have already written T, so therefore, A over 2 to the power of 2n will be greater than 0. Okay. So, if n of A over 2 is greater than 0, that means if it is equal to 0, y equal to 0 means it is on the x-axis. Y is a negative number means it is below the x-axis. Y is greater than 0 means it is above the x-axis or above the horizontal axis. Okay. Therefore, the point A over 2, comma, Fn of A over 2 lies above the horizontal axis irrespective of the values of A and N. Okay. 2n is a positive even number. I can just write because n belongs to the set of positive integers. Okay. So this is the answer for subpart E. Subpart F. Hence or otherwise. Hence means in subpart E we had proved that the point A over 2 comma Fn of A over 2 lies above the x-axis for every value of A and N. Okay, and you may use this feature or the other features of the other subparts, the previous subparts, or otherwise you can use some other method as well to show that Fn dash of A over 4 is greater than 0, where n is a positive integer. And this is the expression for Fn dash of x, which we had proved in subpart C. So I have just brought in this expression, which I am writing. First of all, just copying it rather, because we have proved it. It's not that they have asked us to prove it and we have proved it. So we have every right to copy it now. Equal to n times x to the power of n minus 1 times a minus 2x times a minus x to the power of n minus 1. Okay. Now, since we are required to get, we have to show that fn dash of a over 4, that means x equal to a over 4 is greater than 0. So we will be substituting a over 4 in place of x. Therefore, sorry, I have to put a over 4 in place of x. So it is this way. A over 4, okay, equal to n times a over 4 to the power of n minus 1, a minus 2 times a over 4 times a minus a over 4 to the power of n minus 1. Okay, so this is n stays as it is. A over 4 to the power of n minus 1, I am keeping it as it is. A minus 2 times a over 4 is a over 2. And a minus a over 2 is a over 2. So it is a over 2 times a minus a over 4 is 3a over 4. To the power of n minus 1. Okay, so we have to show that this expression is greater than 0 for every value of a and n. Fine. So since n belongs to the set of positive integers and it is not over here. Actually, a belongs to the set of positive real numbers. Okay. So, and a belongs to the set of positive real numbers. Therefore, n is greater than 0. A over 4, it is just containing 2 marks. So, a over 4 to the power of n minus 1 is greater than 0. A over 2 is greater than 0. And 3a over 4 to the power of n minus 1 is greater than 0. Okay. So, if n dash of a over 4, all of them are greater than 0. So, if you just multiply some positive numbers, the product will be positive. So, if n dash of a over 4 is greater than 0 or n belongs to the set of positive integers and a belongs to the set of real numbers, positive real numbers rather. Okay. So, this is shown. So, we have completed subpart F. Now, only 2 more subparts remaining, subparts G and subpart H. So, let us bring the subpart G first. Subpart G. By using the result from subpart F, this is the result from subpart F, and considering the sign of Fn dash of -1, show that the point 0, 0 on the graph of y equals Fn of x is I, a local minimum point for even values of n, where n is greater than 1 and e is a positive real number. It contains 3 marks. Fine. So we have seen, first of all, let us find what is the value of Fn dash of 0. This is the expression for Fn dash of x. So let me just write this. Okay. A minus 2x and a minus x to the power of n minus 1. So first of all, let us find what is Fn dash of 0. N times 0 to the power of -1. 0 to the power of -1 means the whole expression is 0. A minus 2 times 0 and a minus 0 to the power of negative n minus 1 equal to 0, because we are having 0 to the power of n minus 1, so it is equal to 0. So if n dash 0 equal to 0, and what is if n dash -1? N is an even number, they have said, positive even number. So if n dash of -1 is equal to n is an even number, so -1 to the power of n minus 1 times a minus 2 to the power 2 times -1 and a minus of -1 to the power of n minus 1, which is equal to, now since n is a n is an even positive number, so n minus 1 will be an odd positive number. Okay. So this is equal to -1 to the power of some odd number is -1. So it is negative n, and this is a plus 2, and this is a plus 1 to the power of n minus 1. Okay. So because n is even, therefore n minus 1 is odd. So -1 to the power of n minus 1 is equal to -1. Okay. And 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 n is greater than 0, a plus 2 is greater than 0, and a plus 1 to the power of n minus 1 is also greater than 0. Therefore, if n dash of negative 1 is less than 0 because of this negative sign in front. Okay. Also, we are now using this. E over 4 is a positive number because E is a positive real number. So E over 4 is a positive number. So if n of negative 1 is negative, if n dash of negative 1 is negative, if n dash of 0 is equal to 0, and if n dash of E over 4, a positive number, is positive. So the sign diagram is from negative to positive. The transition of the sign is from negative to positive around this value 0. Okay. So also if n dash of A over 4 is greater than 0. Therefore, the the graph of y equals fn of x has a local minimum point at x equal to 0 when n is a positive even number. So the same subpart G, now we will be doing the II, and it is saying that a point of inflection with 0 gradient for odd values of n. We have to show that this point 0, 0 is a point of inflection with 0 gradient for odd values of n, where n is greater than 1 and E is a positive real number. We have already shown for the I subpart that if n dash 0 is equal to 0. So, and this was the result for the subpart F, that is if n dash of A over 4 is a positive number, is greater than 0. Okay, so I, this one is I. If I'm not showing again that f n dash 0 is 0, because we have already shown that in the subpart I. So, shown and if n dash E over 4 is greater than 0, where A over 4 is greater than 0, shown in subpart F. Okay, so now again we compute f n dash of negative 1, where n is an odd number, positive odd number. So if n dash of negative 1 should be equal to, I'll be just substituting negative 1 in place of x, so it will be n times negative 1 to the power of n minus 1. Since n is an odd number, therefore n minus 1 will be an even number. and a minus 2 times -1 and a minus -1 to the power of n minus 1. Okay. So this is equal to, now -1 raised to some even part is +1. So this is simply equal to n times a plus 2 and a plus 1 to the power of n minus 1. Because n minus 1 is a positive odd number. Sorry. N minus 1 is a positive even number, sorry. Since n is an odd number. Therefore, -1 to the power of n minus 1 is equal to 1, positive 1. Okay. Also, n is greater than 0, a plus 2 is greater than 0, and a plus 1 raised to the power of -1, n minus 1 rather, is greater than 0. Therefore, if n dash of -1 is greater than 0. Okay. So if you want, you can draw the sign diagram for the previous case also, I subpart. So it is x if n dash x. So this one is 0. This side is positive, -1, it is positive, and this side is also positive. A over 4 is a positive number. So there is a point of inflection with 0 gradient at x equal to 0. When n is an odd number. Okay. Consider the graph of y equals x to the power of n times a minus x whole raised to the power of n minus k, where n is a positive integer, a is a positive real number, and k is also another real number. So part H, it says state the conditions on n and k such that the equation x to the power of n times a minus x whole raised to the power of n is equal to k has 4 solutions of x. That means if we graph this and we graph y equals k will be a straight horizontal line. Those two graphs will be cutting at 4 points. Only then we will be having 4 solutions for x. Okay. And if we just try to relate these two, we are seeing if we take y value as 0, we will be getting this equation. X to the power of n times a minus x whole raised to the power of n equal to k. And minus k means it is just a vertical translation. We will be having this shape of the graph, and depending on the value of k, it will be moving up or translated up or translated down. If k is a positive number, then it will be translated down and the graph will be translated down. And if k is a negative number, negative or negative is positive, then graph will be translated up. Okay. So depending on whether k is a positive number, it moves or translates down, and if k is a positive number, it translates down, and k is a negative number, it translates up, just the opposite. Okay, because of this minus sign. Now, this was the expression for f on n of x, and we had graphed 4 different graphs we had changed from the calculator for n equal to 2, n equal to 3, n equal to 4, and n equal to 5. And for a, we had taken the value of a to be equal to 2. But if in case if you have any doubt that what if a is not equal to 2, a is a positive real number. It can have any real, any other value, any other positive value, means it can be an integer, it can be a fraction. So why not try different values of a? If you are convinced that they will be having the same shape, fair enough. But if you have any doubt, at least you can try one more, taking some other value of a. Let me take a to be equal to 3. Okay. And I'll be taking n equal to 2 and n equal to 3. I'll be taking one even value of n and one odd value of n, just to check whether we are getting some different shape of the graph. Okay. So we are taking a as 3. So, okay, let me just escape or let me take another one. Fine. So over here, it will be x to the, I'm taking x to the power of 2 first of all, times a is 3. So 3 minus x raised to the power of 2. Okay. So the same shape for even values of n, the power when it is even, we're having one maximum and 2 minimum points. I may show you. Most probably over here, this is x squared. So for a equal to 2, and this is for a equal to 3, the maximum has gone up, but the shape is the same, and we are having x equal to 0, the 0 comma 0, the origin as one of the zeros, and over here this time it is x equal to 3 has to be, because 3 minus x equal to 0 means x equal to 3. Okay, so these are the 2 zeros, and of course the line of symmetry will be x equal to 1.5. We are not concerned with those, but we are seeing that for even power, it is exactly the same shape. And if you want to check for the odd power also, so then let us go to the next graph sheet, and we will be taking x to the power of 3 times 3 minus x to the power of 3. And okay, let me just, over here the points of inflections are not so very well defined. Let me just change the graph settings. Okay, I can take the, at least minimize the x values, the horizontal axis. it is -5 to +5. I don't know how high it has moved. I can take this as -2 to maybe 15. I'm not sure. Okay, okay, this is better. And you are seeing still we over here for since the n value is odd, so we are indeed having the points of inflection and one maximum point. So it doesn't matter what is the value of E. If n is an even number, we are having one maximum and two minimum points. And if n is an odd number, it is having a single maximum point and two points of inflection with zero gradients. Okay. So the shape is not changing. So that is what we and for this, okay, let us try this one. Let me just change the settings once more. I had taken -2, let me take -5. Okay. So over here, we are having this part we have sketched or graphed the left hand side, and we will be sketching y equals k. So let me just take y equals 5. Okay. So this is the line. And if I just move it, sorry, if I just move this way, you see you don't have any 4 points of intersection. You are having only 2 points of intersection. If you move over here to this place, you will be having a single point of intersection. And for all other points, you are having exactly 2 points of intersection. Okay. So when n is an odd number, you cannot have 4 points of intersection, plain and simple, because whatever is the value of a doesn't matter. Whenever n is a positive odd number, the shape of the graph will be this. Therefore, you will not be having any 4 points of intersection. Only 2 points of intersection will be there, or there can be 1 point of intersection or no points of intersection, because if you just take it above, there will be no point of intersection. Okay. So let us write that. Let us just write that. Probably the graph, the vertical axis is not completely vertical, but assume it to be vertical. Okay. And you are seeing that this one, it is one of the points of inflection with zero gradient is the origin for every graph. Where is it? See, for every graph, it is the origin is one of the points of inflection with the zero gradient. Okay. And let me once more see what is the shape. Okay. Let me try at least. So this is actually a rough sketch. This shape of f n of x when This is x and this is y. When n is a positive odd number, so let me just draw a line. Let me just draw a line this way. Okay. So this is y equals k. And this one is if n of x. I have written this as well. Okay. So we are seeing that wherever I draw this line y equals k, it will not be crossing the fn of x graph at more than 2 points. Okay. So from the graph, it is clear that regardless of the value of k, the y equals k line will not be intersecting the graph of fn of x at more than 2 points. Okay. So we cannot take the condition when n is an odd number. Okay. So let us see what is the shape of fn of x graph. When n is an even number, over there you have 1 maximum and 2 minimum points. So this is one of the n equal to 2 graphs. That is, n is an even number. So these are the 2 minimum points and this is the maximum point. So let us try to graph this. Okay. Okay. And this is the x-axis, this is the y-axis. And there will be one of the minimum points will be over here. So it is somewhat of this shape. Shape of if on graph. This is also graph. when n is an even number. Okay. And now if I draw a line, over here, this line, in fact, this is also having two arrows. Let this be y equals k. Now you see the y equals k line is crossing the fn of x graph at 4 points. So there are 4 solutions for that equation. So when n is an odd number, positive odd number, you cannot have 4 solutions. You can have 4 solutions only when n is an even number. And when can we have, what can be the values of k? What can be the values of k for which there will be 4 solutions? Because if this y equals line is drawn somewhere over here, there will be no solution. But if the y equals k line is drawn somewhere over here, like on the x-axis, even then you will be having only 2 solutions. If it is drawn over here, it will be having 2 solutions. So when is it having 4 solutions? When the k value is between the minimum and the maximum points. Okay. So only when k value is between the minimum and the maximum points, greater than the minimum point and less than the maximum point, do we have 4 solutions. Now, these are the 3 x values that we had got in subpart D. These were the 3 x values for which the f in dash the first derivative of x was equal to 0. Okay, so those were x equal to 0, this one, x equal to a over 2 and x equal to a. So in this case, this will be x equal to 0, this will be x equal to a, and this will be the in-between point, this will be a over 2. Okay. So what is the y value? X value is a over 2. So, but we need the y value. So let us get it. If y equals fn of a over 2 equal to a over 2 whole to the power of n and a minus a over 2 whole to the power of n, which is a over 2 to the power of n times a over 2 to the power of n, or a over 2 to the power of 2n. So this is the y value when x equal to a over 2. So this is the points coordinates will be a over 2, comma, a over 2 whole raised to the power of 2n. Clear? Therefore, the equation x to the power of n times a minus x to the power of n equal to k will have 4 solutions. Only when n is a positive even number and k value should be between this x-axis, that is k equal to 0, it should be greater than 0, and it should be less than the maximum value, that is a over 2 whole to the power of 2n. Okay. So this is the final answer. This is the final answer. I can just take this and I can write this is the final answer. Okay. So students, we have completed question number 1 of this paper 3, and we will be solving the question 2 in our coming session, in our next session. And thank you for staying with me till the end. I'm Nilanjana Sanyal. I tutor online, in fact, IB Math E, SL and HL level students from inside and outside India. And I'm starting my batch for the online group tutoring sessions for the freshers who have started their grade 11. Okay. So, and they will be small groups. So in case you are interested in joining my group, you may contact me. You are seeing my email ID getting displayed. You are seeing my WhatsApp number getting displayed. You may contact me for more details. Okay. So we meet again very soon in our next session where we'll be solving the question number 2. Till then, bye.